All right, 5-minute lessons, vector style. Let's go. Okay, we're going to start by explaining how great vectors are and how useful they are. So let's say somebody walked in a 30-degree angle north of east at 10 miles per hour for an hour. So they walked 10 miles. Okay, well, we can break that situation up into its components. Okay, and to do that, you just got to think about this as a right triangle. So this is the x and this is the y, and you'd say cosine of 30 is x over 10, and sine of 30 is y over 10. So you end up getting x is 10 times the cosine of 30, and y is 10 times the sine of 30. And let me pause that real quick. So what we get is 8.66 for x and 5 for y. And that should make sense. I didn't draw the best picture. If you think about 30 degrees, more of it is going in the x direction than in the y direction. How much? Well, that's the nice thing about vectors. A vector can take a situation and apply both the direction and the magnitude. If I did this, the square root of 8.66 squared plus 5 squared, you better believe I would get 10, because the length of this vector represents the force or the speed or whatever magnitude of force we're trying to relay from the components. So here's where this really starts to become convenient. If you have any angle that's started from the standard position, okay? So let's say you had a 245 degree angle and you have a force of 100 pounds and you want to break that up into its components. Well, I mean, I do want you to know that all you're doing is a little trig. Here's your x, here's your y, here's your hypotenuse. Well, your x is your adjacent and your y is your opposite. So like you just saw that we did, but you can go straight to the answer now. If you wanted to break that vector into its components, it would be 100 times cosine of 245 and 100 times the sine of 245. So you always do your magnitude of your force times your direction angle from your standard position. Let's fill that in. All right, so when you throw that in your calculator, make sure it's in degrees. And this is what you get for the decimal version of the components, which makes total sense, okay? We're going left at a rate. There's 42 pounds of force being pulled in this direction, and then there is 90 pounds of force being pulled down. And that's figuring out the components given the magnitude and the direction. Okay, so how do we use this? Well, this is where you start to see where if we just break things up into their components, most things in science are just a combination of forces. And all we want to do is add their parts that are parallel or like each other, okay? So this is like a classic example of applying this physics problem. So what's going on here? You got Sahana is walking at a vector of 3, 4. So that means she goes right 3 and up 4 in this direction. Now, while she's doing that, Hurricane Ian comes her way and blows at a rate of 100 miles per hour in the easterly direction. So look, this is a huge vector. Its magnitude is 100 and its direction angle is 0, in case you were wondering. Okay, now, so what's happening? Well, both of these forces are enacting on Sahana. Her feet are moving her in the direction 3, 4, but the wind is pushing her in the direction 100, 0. So if I take her feet and I add the wind, That's going to give me my resultant force. So this yellow vector represents, that's actually where Sahana is going to go, believe it or not. She's trying to go where the red is looking, but she's actually going to get pushed all the way where the yellow ends up because it's a sum of forces. So what is this yellow vector? Well, all we do is just add the components. The yellow vector is 3 plus 100 and 4 plus 0. Okay, now, what was the actual direction she was traveling? To do that, we're going to need to use trig. Just think about this triangle. This is 103. This is a right angle. This is 4. So we're going to do tangent of theta is 4 over 103. And you might read some book will tell you theta is the tangent inverse of x over y, but you don't need to remember. You don't need to memorize that. Okay, sorry, of y over x, of y over x. Let me give you that. Okay, I thought I had done it wrong, but then I realized that answer makes total sense. Theta is 2.22 degrees north of east. So it pushed her off her course pretty significantly, but that's a big wind. It's a hurricane after all. Okay, now how fast is she actually? Well, here I want you to know the magnitude of this red vector is 5. If I did the square root of 3 squared plus 4 squared, you might recognize that as the Michael Jackson of right triangles, and that's going to be 5. So Sahana was walking 5 miles an hour, but the wind was blowing her at 100 miles an hour. So you might think she must be going 105 miles an hour. Not true. Not all of the wind was going in the direction that she was going in. That's kind of like the beauty of this. So to figure out how fast she was doing, we're going to take the magnitude of the resultant vector, 103 squared plus 4 squared. And what you get is 103.1 miles per hour, which makes total sense to me. She was walking 5 miles an hour. There was a 100-mile-an-hour gust. So that propelled her to go 103.1 miles an hour because not all of the wind was going in the direction that she was headed. That's what I want you to understand the most about this. Okay, love this stuff. Hope this helps. Boom.